Sound is so good. Cracky like Leo's personality. Okay, let me put these bad boys in. There we go. How about now? Is it better? Now is better. Okay. Mr. Jack Levin is in the house. Oh, okay. Okay. Yeah, I'm sorry. I don't have my microphone. But I really wanted to do this stream. Perfect now. Okay. Decent sound. Rolando is in the house. Critical Mass, Ferrex Thinker. Oi. Only celebrities. Only celebrities. Guys, we have so much to talk about. I'm gonna take the liberty to dive right in. We are going to talk about the X1 blockchain today for a change. And it's secured by the Lachesis consensus algorithm, which is using DAG and leveraging transformers. We're going to talk about today, artificial intelligence at the end, for aid in the consensus decisions. So these two topics go very well in hand together. Now, there's been a huge amount of confusion circling around the topic of DAGs. DAG, gamut, and people say that DAG blockchains are not real blockchains, and somehow they are less immutable and less decentralized and have less censorship resistance. I, Zen Zhu, the high priest of Zen, self-proclaimed, is hereby calling bullshit on all these statements. And I hope to clarify a lot of things here today, and also delve into some interesting stuff with the AI. So let's dive right in, guys. What do you say? Dag Navit. Okay, so why DAG? Let's begin there. Why even think about DAGs? Better yet, implement it as part of the consensus machine for X1. Well, it does give us many advantages, such as, and the main benefit is scalability, because DAGs can handle a higher transaction throughput compared to, let's say, traditional blockchain structures. And this is because in a DAG, the transactions can be processed in parallel, which is reducing the congestion and improving the speed. So throughput is a measure on how many units of information a system can process in any given amount of time. So we can process transactions faster, leading to lower fees. We get faster confirmation times because transactions can be confirmed and also reach finality very fast, because transactions don't have to wait for a block to be mined. And I will explain this in detail. So ultimately, we can have faster TTF, time to finality, near instant. And this is very cool. And that can also be energy efficient, etc., etc. Now, there's a lot of benefits. But if you doubt this, before we go into the technical details, just look at phantomscan.com and go to top tokens. And this is something we see on every chain that Zen is on. We've been with Zen and FM Zen in particular on Phantom, absolutely dominating transactions with over 90% of their whole chain usage, which is absolutely nuts if you think about it. And on Phantom, and this is the code base, the Phantom code base that we are forking for X1 using this Lachesis consensus protocol, which, by the way, does not, I repeat, does not make us an L2 on Phantom, FFS, for fuck's sake. So this is just in the last 7 days, but it's been looking like this continuously throughout for over a year now. And in our opinion, it's been the chain that handled the stress test absolutely best from our deployments on these 13 EVM chains. They didn't censor us. They didn't censor contract like Dodge Chain did. They didn't crumble under the load like Polygon. They didn't manually adjust the gas fees like OKX. The chain can handle Zen just fine, which is a great badge of honor for the Phantom and the Phantom team. We have to give them tribute to. So there is something there with DAGs. And to be honest, we discovered Phantom by shitting on it with Zen, like we've done on every chain. And then from doing that, we realized, wow, this is really good. And then that led us to dig deeper into why it was so good. Jack likes DAGs, he says. So how can this be? Like, let's not just assume that these benefits do exist, but let's go into the levels, as we always do, on the features of DAG. Let's understand it and how it's different from other consensus mechanisms and the data structures. I'm very excited about this topic. And yeah, because I think like a lot of people don't really understand it. It's so complicated, and people, even like the PhDs, they're very bad to explain it. So it's not that strange that there is a lot of confusion. Okay, but let's just break this down in the various different thought experiments. So in a regular, is good size, guys? In a regular blockchain, let's say, let's call it regular, the blocks that count are in a sequence. So with each block pointing to the last, and note here that the time is in the upwards direction. So this is what we refer to as sequential block production. So this is the data structure, if you will, that Bitcoin uses for the formation of blocks that Ethereum later have copied. So they are both following this model of structuring this data, even Solana as well. And as we know from Bitcoin and Solana, as an example, forks happen all the time in that there is a conflict over what the next block should be, which needs to be resolved, of course. And eventually, one side ends up counting. And with Bitcoin, it has this longest chain rule, which is part of the Nakamoto consensus model. So the valid chain with the most accumulated computational work is considered the true and valid chain in Bitcoin's case. Solana, forks happen all the time. And that's settled by the validators. It's a very computational heavy exercise. And most of the times they handle that very well, and sometimes not. So forks, you can say, threaten the security in a theoretical aspect and practical. And we have to somehow slow things down a lot to prevent them happening too much if we're not redlining the service like Solana does and are okay with that. And that's part of the reason why Bitcoin has 10-minute block times as well. Solana only has 400 milliseconds, but they are, on the other hand, very okay with crashing. So it seems. So a thought experiment now is, what if both sides of this fork could count without threatening the security? Then we could produce blocks much more quickly. And this is sort of what happens with a DAG protocol, because we have these blocks, or more correctly is to say these events. They are now allowed to have multiple children and multiple parents. And the resulting structure is a directed acyclic graph. So again, this is just a simplification showing how the data structure can differ. But what to bear in mind is where and how it is used. And I will show you this in detail. Block production is not necessarily what this data structure is used for. But with DAGs, this data structure can be used even before blocks are produced and part of the consensus. It's not like DAGs are actually continuously forking, of course. I will explain this in detail. But if we just look at the name, directed acyclic graph, what does it really mean? So a graph, it's just a bunch of nodes or blocks with edges, arrow in between them, okay, as we see here. It's directed because the edges, the arrows, have a direction to them, okay? It's acyclic because they're all pointing in the same direction, more or less, which means we don't get cycles if they're pointing in the more or less same direction. So the idea here is that for a protocol like Bitcoin, you want to do two things. Okay, number one, you relay the set of transactions, and number two, you also establish consensus on the ordering of these in the verification of transactions and production of blocks. DAG protocols, they don't let the block's role in establishing consensus get in the way of its role of relaying transactions. The DAG just relays transactions together with some minimal ordering information required to make sense of them. Then a consensus protocol can be carried out on the DAG structure to order the transactions at no or little communication cost. So punchline here is, in terms of throughput, you've stopped consensus being a bottleneck in the consensus of block production being a bottleneck. And what I just say here is fundamental and key, but the significance of that might not be clear to you at this moment. And you maybe have to watch this again from the beginning later to understand what I just say. But we're going to dissect what I just said. And remember that this is very simplified comparison of data structures and how that fits in with how the chain actually works and what the data structure is used for, that we need to define. Yeah, I'm just checking comments, guys, just to see that you're okay. Seems like you're okay. Let me know if the sound goes badly. But let's start with looking a little deeper into the limitations of these sequential block production. So with Nakamoto consensus, you can think of it as you have this container, which we can call a block. And that has a particular limit in size. Specifically for Bitcoin, it used to be 1 megabyte. Now it's 4 megabyte. With Ethereum, it's much smaller, and we measure it in terms of size in gas. So you have 30 million gas units per block. So in a traditional blockchain, every block points to another block, which is what we call a linked list. So a linked list is a list of data elements which points in sequence, 1 to 2, 2 to 3, 3 to 4, etc., etc. And why they are so good, it's because it makes this data structure very robust. And the reason it's robust, it's because should you try to disrupt the middle of this data structure, it affects the rest of the connected blocks. So you have a hash of one block, and then you hash that together with the hash of the next block, etc. And that's how immutability is created with this linked list with SHA-256. And this is what's happening with Nakamoto consensus. So the block has a limited space in byte size, and it has a time frame when it has to be produced. And in Bitcoin, it's 10 minutes, and Ethereum, it's 12 to 15 seconds. So as you know, and as we talk about all the time, what we and everyone else is trying to solve is this blockchain trilemma. Like, how can we make a chain that is scalable yet decentralized and secure? With traditional Nakamoto consensus, we can be so brave or so daring to say that scaling is impossible because you're limited by the block size, the block time, and and fitting into this assembly line, if you will, of sequential block production. It's almost like Henry Ford said when he invented mass production of cars. You can have any color of the car as you want, as long as it's black. It's sort of the same thing here from the perspective of transaction. It's like you can get into any block as you want, but it's got to be in this order. So there's no way to scale. And this is why both Ethereum and Bitcoin are now obsessed with L2s to solve every other use case that's not store of value. But on the L1, there is this time frame and the bidding auction with fees to get included in the next block. So if you bid too little, you're not going to be included. If you bid above, you're likely to be included. And this bidding war, it's what's caused the transactions to be very, very expensive. So now we can see that the GUI is 54 on on Ethereum at the current moment. And if we look at mempool.space, yeah, we just had a block produced with 80 sats per virtual byte. So now when we see Bitcoin price is coming up, it's going to have effects for the whole cryptoverse. My prediction is that there's no other possibility if Bitcoin gets popular that we're going to see much higher prices because people want to be included in the. It's like it comes down to like, what are you willing to pay for your transactions to be included in the block? That's what it comes down to. It's a block space auction. And the reason why this happens, of course, is because the data structure is linear and consensus has to adjust to that. So it has limited space within the block, and it has a time frame for the block creation it needs to stick to. The major difference with DAG is that DAG doesn't have this concept of a block primarily, okay? It has the concept of transactions being observed by nodes. So I exited the stage. Am I back? I think there's a glitch. I'm back. Okay. Video did an AVAX. Exactly. Did X1 just go down? Yay. Okay. Blow up the screen text. Gotcha. Thanks for feedback. Bilmont, good to see you. See you, buddy. Okay. Continue. Good to see you guys. So why is this so? Why is this so? Let's compare these two different systems in terms of transaction finality. Can't see, blurry. Okay. Yes. So how do we reach transaction finality? In Nakamoto consensus, with sequential block production, transaction finality happens. Let me zoom in. Transaction finality happens after the block is produced, okay, proposed and settled. So you have block first, finality later. In traditional blockchains, you have a block producers, like with Bitcoin, someone who solves the cryptographic hash, proposes a block. That block is then voted by at least 51% of the network. If it's legit, it gets voted into the blockchain. And that's what makes it slow, because the block needs to go everywhere and get voted in. So you have a transaction, something, there's a block proposal, something, you then reach finality of your transaction after some confirmations, like 3 to 6 confirmations. So that can be up to an hour or even more. So the thing here is that there is a time in between here for block consensus, but we can also call it transaction finality delay, in lack of a better word. So meaning that all transactions in the block are final once the block reaches finality. So you have to wait for the network to push around these blocks, have them unpacked, ran through, verify those transactions by other nodes. Now, with DAG consensus, DAG Gummit, we instead do a little different. So there's no block finality delay because finality is part of the block creation process. It happens during somehow because the block is not proposed. Even in Solana, the blocks are proposed first, and then there's voting and finality. But with DAG, voting occurs on the transaction level. So every transaction is voted for, and then when there's enough transactions, they get assembled into a block from the DAG. So the block itself doesn't need to be finalized because all the transactions are already final. All transactions within the block has already been checked before creating the block. So every transaction is voted for through the consensus mechanism, where 2/3, in our case, have seen and observed the transactions and verify it. And that's how we reach consensus. So in our case, we have a time frame of half a second. So where we collect all these transactions, and we do all the voting before the block is produced. The voting is then done, consensus is done, the block is then created, and it's no longer needed to be voted on, because the transactions within it has already been finalized. And that's why it's so much faster. I'm going to show all of this step by step. But this is what we mean when we say that we have near instant finality. The final result is a block that has all the transactions. Good to see you, Aidan Rasic, Simple Waters, all the celebrities in the house. So block production in Phantom, it does not require further validation. On other networks, this is needed because transactions are validated after the block is created. In DAG, transactions are validated before it hits the block. And while on this topic, just to mention, for X1, we don't have a hard-coded block size limit even, because the sizing of the block is set by the rate of transactions that can fit into half a second time period. So there is a practical limit, of course, but it's not predefined. So also a single transaction has 10 million gas, but there's no limit of number of transactions that can be there. There's this terminology of emission time, like how quickly can events be observed. So if events are observed very slowly, blocks will end up with a bunch of transactions. If it's fast, it will have less. So anyway, this is the main reason how a DAG really differs versus traditional Nakamoto consensus, and the reason why it can be so much faster. Because we can therefore achieve near instant finality because transactions are finalized before block productions, and also due to the DAG consensus. Transactions can be propagated in parallel versus in sequential order. Asynchronous BFT, ABFT, as we say in Sweden. So that's what I'm going to talk about next. Now, in the real matrix, this is also a bit of a simplification. Okay, there are a few more details in exactly how this works and what's happening with terminology here, such as these transactions are actually optimized and packed in something called event blocks, but the principle is the same. So try not to confuse those event blocks with final chain blocks. Unfortunately, block is a very popular word. I think people are going to name their kids block soon because part of all this confusion is probably because DAG creators also name the block for everything. There's event blocks, there are final chain blocks, and there's Nakamoto blocks. They should just call it something else. But it is what it is. So let's talk about asynchronous Byzantine fault tolerance, because this is here we got, would be nice if every transaction was its own block. Why not do it that way? I guess storage efficiency. Yeah, but if you can fit thousands of I'm going to come to this later. I'm going to show you exactly. If you can fit more in one, you want to be as optimized as possible. This is the short answer. So yes, asynchronous BFT. Now, Bitcoin and Ethereum, they are so-called synchronous systems. And as we know, synchronous systems, they can be either decentralized and secure, but then very slow. Or they can be, for example, decentralized and fast, but not so secure, et cetera, et cetera. So Phantom blockchain wanted to solve this by using this asynchronous Byzantine fault tolerance consensus that allows transactions to be processed asynchronously. So that the transactions must not follow a particular order, which increases the speed and the throughput of transactions compared to synchronous systems, BFT ledgers, as I mentioned before. And again, throughput is a measure of how many transactions are completed within a given time frame. So Lachesis is the name of the open source consensus protocol of Phantom blockchain. And that's an asynchronous Byzantine fault tolerant system. So what does that mean? It means, and I gave some example in my last stream, but a network is said to be a Byzantine fault tolerant system when its nodes can reach full agreement on any transaction, even when there's a disorder from an aspect of the network. So when the network is attacked or there's a malicious actors. So with this structure, nodes in the Phantom blockchain can validate event blocks that contain transactions without any restriction on timing. And this makes the network very fast with a high TPS, transaction per second. Yet, you remain the decentralization intact. So when a transaction is confirmed in Phantom, it achieves this finality. And you can't change it and it can't be reverted. And in this case, the finality is for a transaction to be completed is just around 1 second. So it's super fast. It's super fast. So the DAG is, you can say that the DAG is first of all a data structure. It's another data structure. It's another way of structuring the data. In computer science, data structure refers to literally how you save data on a hard drive. But more importantly, yes, the output is a data structure from what's happening on chain, but the assembly of events in the DAG format is what triggers the consensus. So it's only when the data is arranged in this DAG structure, parents, which I'm going to talk about what that is, parents and children know of leaves, then we have this consensus decision. So ultimately, the output from the consensus function is something like, the system asks, is this event valid, yes or no? If it's valid, then it's assembled. And they're assembled in the DAG, and they are observing each other. And at the end, we then use the DAG to make that the consensus decision. So note that this has in itself, like the way you structure this data, very little or nothing to do with immutability, censorship resistance, or decentralization per se. And it ever says like generalizing statements like blockchains are inherently decentralized, censorship resistant, and immutable, and DAGs are not, are just stupid little cunts because they're just trying to get the attention for their token or something, because it doesn't make sense whatsoever. DAGs just have another method of data structure, which is the basis for consensus. So generally, with Ethereum and Bitcoin, the consensus mechanism has to receive a block from a validator that is acting like this block proposer, right? So it's a computer receives all the transactions, puts them in a block, proposes that block to the rest of the network. The rest of the network will then either vote on if this block is accurate or not. And if the majority of the network agrees that it is, it will add this block to the chain. But the way Phantom or DAG works is that every transaction is entered into this mempool and is observed by the network of nodes. And each node actually casts a vote on the transaction itself. And then you're building this data structure from that. And that is then used to make the consensus decision. So the difference between the DAG data structure and a regular blockchain, which is a linked list, is that DAG is a multi-dimensional linked list. It has many parents and many leaves. So let's look at the properties of DAG, because there's a lot of new terminology that might be confusing as well. Let's look at the elements. So first, because we're talking about nodes and edges and parents and children and roots and leaves. So what the hell is all of this? So first of all, when we say nodes in this case, don't confuse that with chain nodes, the one you're running on X1 right now. Servers reading and validating the chain. Here, a node represents some object or a piece of data. And in our case, this will, for example, in most cases be transactions that we in the DAG will call events, and also observations of transactions, which are also events. So we have this thing called directed edges, so or arrows in between two nodes, and what they are doing is symbolizing some kind of relationship between these nodes, these two events. So in our situation, it means that this arrows means is observing. So 2 is observing 4 here. So arrows in a DAG, they can also not form a cycle like we talked about before. Therefore, in the name, directed acyclic. So it follows some kind of direction in time, and it can illustrate this connection between two nodes that an event has observed another event, for example. Then we have this thing called a root node. So a root node is at least one of the nodes that will have no parents, and that's the root of the DAG. We have leaf nodes, and one or more of these leaf nodes will have no children, and they are called leaves or leaf nodes. Now, unlike traditional blockchains, which which organize the transactions in the sequential block, the DAG arranges transactions in this graph-like structure, where each transaction is linked to multiple previous transactions, and they're forming this DAG. So you can say that in a DAG-based system, each transaction refers one or more previous transactions, creating a network of interconnected transactions. And they are typically, there's no distinct like blocks or miners in the construction of these data structures. Instead, transactions are directly added to the DAG structure. So transactions are then validated by referencing a sufficient number of previous transactions rather than through traditional consensus mechanisms like proof of work. And here's another way to describe it, which I think is very good. So we have 4 different participants here: validator Alice, Bob, Carol, and Dave. Now, this is a DAG. Okay, so each number here is an event, and that can be a transaction or an observation of a transaction. So A101 here, that is a root because it was Alice's first event. A102, B101, C101, and D101, they are observations of this root event. So the arrows are pointing to it. These are leaf events. And altogether, they form a data structure. So this is a multi-vector chain of events. When you collapse this segment of this DAG, you can then create a block which contains all these transactions and observations of transactions. So that's the relationship in between. So the DAG data structure for processing transactions by observing these events and building these trees. What's cool with DAG is that blocks only get created when transactions show up. So there's no waiting period for blocks. There's no defined time limit that they need to keep. So you can say that a DAG is a bunch of parallel blockchains created at the same time within a particular time frame. And this allows for this parallel execution. And a linked list on Ethereum, for instance, it requires the node to validate the transactions in the sequence. And you can say pretty bluntly that that's like a single-threaded execution environment. So DAGs are faster, and because the reason is that any transaction that shows up in the middle of a block does not need to wait for other transactions to execute, because it just creates another branch. It creates a parallel branch on an execution pathway, and that's how it's stored. Whereas with Ethereum, every transaction has to execute one after the other. So with a DAG, we have multiple branches. It's growing like trees, and that's what makes it so fast and expensive. You don't have to wait and pay more to be included, because you're likely going to be included anyway. Now, that's just to get you some familiar with some terminology and how things are working together. So let's talk a little bit about the Lachesis protocol, and then show you exactly step by step how all of this works in a process. So, because now when we know like the benefits of DAG, the differences between DAG and sequential data structure, when transaction finality occurs, etc. Let's talk about like just the engine of itself. And the engine is the Lachesis consensus protocol. And it's an open source software library. It's used for creating consensus in a decentralized network. This is what Phantom is using. It's a DAG-based ABFT consensus protocol with guaranteed finality. So what does that mean, really? You say that Lachesis is asynchronous. This means that participants have the freedom to process commands at different times. So we can do this simultaneously without having to wait for each other. It's leaderless, and this is important to think about because we're going to reference Solana a lot going forward. But this is leaderless, so no participant plays a special role. And each node participating in this consensus protocol is equal and does not need to fulfill a specific role. It's Byzantine fault tolerant. It supports 1/3 faulty nodes, including malicious behavior. So even if 1/3 of the nodes fail, so-called clear nodes, the consensus process will still function. And it's also final. So the output can be used immediately. So there's no need for block confirmation, which means that the output is immediately usable. The block confirmation is not necessary because the transaction became final in just a second. So we call this near instant finality. So this is what the Lachesis library out of the box is delivering. I made this model very quickly. I'm not so proud of it, but just to show some kind of just some kind of relationship between events and what's really happening. So what's happening is that each Lachesis node, they store a local directed acyclic graph, a DAG. They are composed of event blocks, and each of these event blocks contains transactions. So the Lachesis node then gossips and synchronizes these events known as DAGs with each other. And the terms event and event blocks, again, they're sometimes used interchangeably. And this is there's also this thing called happen before relationship. So it's using so-called Lamport timestamps that is used to calculate an exact final order of events independently on each node. That's not something you have to think about now. I'm just mentioning it because it's good to have it mentioned. It's not using some kind of synchronized timer. It's using Lamport timestamps. But anyway, these events are divided into confirmed events and unconfirmed events. So new events are unconfirmed, and we are usually like events from the past 2-3 frames are all confirmed. So I'm going to talk about frames a bit later. So for confirmed events, honest nodes can compute the exact order. Unconfirmed events can only be partially ordered. Now, consensus results in batches of these confirmed events, while each batch of event is called a block. So block, or this is finalized blocks, forming the final chain. They're calculated from these event blocks and on each node independently. So unlike with normal proof of work or synchronized BFT, these nodes don't need to send these blocks to each other. So only these events are synchronized between nodes. And validators don't need to vote on concrete state of the network, but instead they periodically exchange transactions and events they observe with peers. And also one thing to mention that that if you're new to this, I wouldn't think about, but I want to mention it anyway. Like unlike synchronized BFT, like PBFT, for instance, Lachesis, they don't use new events in the current election, but instead they're used to vote for events in 2 to 3 previous virtual elections simultaneously. So that's what leads to a smaller number of created consensus messages, because the same events is reused in different elections. And that's why Lachesis achieves a lower TTF, time to finality, and a smaller consensus overhead compared to synchronized BFT. But forget about that. What I want you to take away from this is that something is happening up here where we have the concept of a DAG, but down here, it looks pretty much sequential to me. And this is the relationship that we're going to talk about next. So that's the theoretical function of Lachesis, which is the consensus mechanism, the engine of the chain. And if you want to dig down, you can read the Lachesis paper. It's very interesting how it all works. But let's put this. Let's try to make this a little bit more clear. So let's look at this in the perspective of a transaction lifecycle. So because now we know that Lachesis and DAG tech for processing transactions and finding consensus, but how does this all fit together? So we're going to look at two examples, one more simple and one more detailed. But it's not more simple, it's not more difficult than the fact that you have a user send a transaction. He sends some Dogecoins from A to B. That transaction leaves his MetaMask. It goes to a mempool, the RPC closest, and the RPC accepts it. It runs some verification. It checks that, is this the proper gas limit? Does he have funds to pay the gas with? What's the GUI? So it does all of this first step verification. And then the peer-to-peer network broadcasts this to every node, which has a mempool. So it's just a queue of all these transactions. And most nodes have this. And some might not have it, but that doesn't matter. So all the nodes that have it will try to process it and create this transaction into an event. They all compete for who can do it faster, of course. If one or three nodes does it at the same time, it's fine. You just have duplicate events on chain. And this is where DAG structure is produced. The event is created. So that transaction is then voted on the rest of the nodes, which is part of the consensus, and using the DAG to make the consensus decision. And then a block is created independently on each node. That's important that's an important distinction I'm going to show next. So the block is a record that can have one or many transactions packaged under one block ID. So it's not more complicated than that, but we're going to look a lot deeper in exactly what's going on and when. Are you with me, guys? Fucking hell. Is this exciting or not? So, clear note. Asynchronous is such a sexy word. Yeah. All right. So what's going on here? Let's make a simple example, just to dumb it down as much as we can. So in this example, we have one network, we have one transaction, we have three nodes. So that's two more nodes than Jack's X1 chain running on his one AWS server. And we need 2/3 majority to settle finality, to reach consensus. So what's going on here? We have this one transaction, and all three nodes, node 1, 2, 3, bam, 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 they see it at some time. When they see it, doesn't really matter. They see it when they see it. So every node has a mempool. So what is this mempool? It's sort of a segment of memory allocated for the mempool. So mempool is a buffer of memory to have room for new transactions coming in. So every node has this local mempool, you can think. And the transaction is then broadcasted to every node using this peer-to-peer gossip protocol, which you know all about. We covered that a lot last time. But the transaction is not verified yet, because here each node does this verification check, right? Again, so they check, can this transaction be executed? Does the user have enough funds? Is the signature correct? Is the nonce properly sequenced? And this is where double spending is also checked against the world state, because where the nonce is checked, like if it was used or not. And this is the same process as Ethereum. And I showed in my last stream how Ethereum and Bitcoin checks double spending in different ways. But Ethereum uses this concept as nonce, and we're using the same code as Ethereum, so there's no difference there, as well as Phantom. They use the same code as well. But they check that, and all checks verified, look good. What happens then is we have this event creation. So a node, whoever is faster, produces the event, and this event, again, it's an act of observation and verification of a transaction, which is saying, I have seen this transaction, I have validated it to be secure, and I put my stamp on it to say that this is a true one. So that creates a node in the DAG data structure, okay? And what happens then is this happens independently on each nodes, and then you have this, you can think of it as the nodes are exchanging these observations with each other, event observation interchange. So this event will be broadcasted to the other two nodes, and they will exchange their respective observation with each other. So the other nodes will see that you have it, they do the same thing, and now you have two events. So the first event came from a first node, the other event is broadcasted. You now have three nodes with at least two events each that are forming these DAGs. So we are now they are now the mothers of the DAG. They are mother daggers. So all these three nodes, they now agree that the DAG is satisfactory, A and B events. Nothing else is needed because they both have seen it. The A and B A event is pointing to B event, or vice versa. So even though the second node here didn't do anything, but he observed what the other two nodes did and verified those. So he also builds this DAG on his node. So and those transactions are now locally verified on those different nodes. Then comes the consensus part of it. So the system then checks if those events for that particular transaction has satisfied the 2/3 requirement. So once the node sees A pointing to B with a weight of 2/3 stake of the network, like if that's true, then the block is produced, what we call the final block. So the network then produces a block. So every node 1, 2, 3 produce a block independently, locally. They don't need to receive this final block from someone else, unpack it and verify it, because the verification, observation of events already happened here. So they build this block themselves, but it's the same block. But what's important is the transaction validation. So we're focusing on the transaction itself rather than the block for consensus. And this is what makes the chain so fast. And once all these nodes synchronize the DAG structure, which means they come up with the same decision and they agree on the consensus, that means that the block is produced and a block is final. So the final version of data produced is a block chain. So transaction instantly, the transactions are instantly final. The block, so no, the correct way to say it is transactions are near instant final. The block is has instant finality. So because the blocks don't need to be pushed around, because all the transactions within this block has already been verified. This is part of the main confusion of the difference between Nakamoto consensus and the block production. So it's almost like it's so efficient, this process. So it's almost like Nakamoto consensus is like driving an old truck, and DAG consensus is like a fast Ferrari. It's like super efficient and super fast. So just in summary, what happens here? When we say that transaction is finalized in the DAG system, you have a bunch of transactions coming through. User ABC, they're all sending some cryptocurrency. They enter into a mempool. All the nodes see those transactions in the mempool. Every node has their own mempool. Each transaction is observed, and also a hash is generated. That hash is then gossiped across in the network. All the other nodes see it. There's a timestamp with their own hash, and they build this DAG graph. And once you have enough observations of particular events and of particular transactions, you end up filling a block. But there's a few things to underline here. Like number one, consensus results in batches of confirmed event blocks, where each batch of event is called a block. Finalized blocks forming the final chain are calculated from event blocks independently on each chain. So as you remember from before, this is a simplified example, but the concept of event blocks can actually contain more than one transaction. Unlike proof of work, round robin, proof of stake, coinage, proof of stake, and synchronized BFT, Lachesis node don't need to send the blocks to each other. Only the events are being synced between nodes. Validators don't vote on a concrete state of the network. Instead, they periodically exchange observed transaction and events with peers. So this is, as we pointed out, the main difference from Nakamoto consensus. But then there's also like various stages. This is still very simplified, but in general, this is how it works. But there's various stages of this consensus. You have this thing called atropos, for instance. So atropos is one of the final stages for this block production. So it's the assigned consensus time through Lachesis consensus algorithm is utilized for determining the order between event blocks. Atropos blocks form a main chain, which allows time consensus ordering and responses to attacks. So you have Atropos block, Atropos block, Atropos block. This build the main chain. That's just various stages of this block production process. But that's like not something you really need to think about. But this one, I think, explains the relationship between the DAG consensus and the final block production very well. So here we can see we have these root events. Okay, so A0, B0, and C0. Now these root events are being observed by B1, C1. So B1 is observing A0 and B0. C1 is observing B0 and C0. B2 in turn is observing B1 and C1. And now it's great because now we have 2/3 majority, and this batch of the DAG can be then packaged into a block that then creates the blockchain. So this is a very good image, I think, that describes this whole concept. So this is a block, this is another block, this is a third block, etc., etc. So yeah. Okay, another thing I want to point out with this is this. So what we can say is that the DAG is a data structure that links consensus to transaction validation. A DAG is used for consensus creation to build a block, and it's doing it ahead of time, right? So before the blocks are produced, every block is then final because every transaction in the block is already final. Whereas with Nakamoto consensus, blocks are not final, they need consensus first. So is DAG then a blockchain? Like DAG in itself is not a blockchain. It adopts the data structure that is used for consensus. So a DAG is a description of how consensus produces the outputs, which is then saved into blocks. So in Phantom, if you're comparing DAG to a blockchain, it's just wrong. The output of Phantom is a chain of blocks or a blockchain. The DAG is the consensus. But blockchain is produced from this data structure after the consensus has been reached. So we can also say that X1 is a blockchain using DAG tech for consensus. That would be a correct way to say it. So a DAG is a description of how consensus produces the output, which is then saved into blocks. So And again, ultimately, you can the output of the consensus function is like, is the event valid, yes or no? If it's valid, then it's assembled and they have observed each other. And at the end, we have this DAG that makes that is something that we can make a consensus decision on. And we can actually see this, like if you go to the fact that blocks are actually produced as a blockchain. If you go to go/x1 in our repo, you will see that there is a lot of Ethereum code already, and this is an example of it. So you can see that this is the exact same code base that Ethereum uses to produce a sequential blockchain at the end. So this is the code specifically that adds a block to the chain using Go Ethereum. So Go Ethereum is Ethereum core blockchain code. It literally builds the exact model of Ethereum blocks after the DAG is confirmed. So you can imagine Phantom being a consensus mechanism on top of Ethereum core. Phantom blockchain follows Ethereum blocks. They look the same and they use the same codes, which makes sense because you don't need to reinvent Solidity or block storage just to create a block. Just how blocks and more transactions within the blocks are validated. So DAG is not a blockchain is a false statement. The output is a blockchain. You use EVM code for making a block. It's the same. DAG is the consensus mechanism for decision making of what's true or not on the blockchain. Bitcoin uses another consensus mechanism. So you will see this, and you will see a lot of other Ethereum code within the repo. So the DAG is the consensus. It instructs Ethereum code to forge a block that will link the rest of the to the rest of the chain, and that is Ethereum compatible. So number 3 thing I want to point out, that's also like, if you still doubt that, you can just go to the Explorer and you will see that every ID has a block number. So it means that the final blocks are sequential, one after the other. You can't have a block in the past that has an ID number versus one in the future. So if you either go to X1 testnet or to Phantom Scan, you can see that the final result is a blockchain, but the creation of a block is done through the consensus mechanism. So using a DAG, it's nothing more than using different data structure and having transactions validated before they get inserted into a block. But the output is the data structure, but the assembly of events in a DAG format, it's what triggers the consensus, if that makes sense. So the blockchain that's produced at the end still has immutable data. Decentralization and censorship resistance in each case depends on the number of nodes and how you determine that consensus, not what the data structure you use. So the implementation of this is what makes a chain centralized. Like if you have a company that owns half of the validators, then their implementation is centralized. The distribution of nodes is what determines if it's centralized, not the structure of the data. It's like Jack said, you can create an Excel spreadsheet and make it centralized if you want. The data structure itself and how the data is stored has very little to do with decentralization in that sense. So a blockchain is just a linked list. It's just a bunch of blocks. They each point to each other in sequence. A DAG forms a tree. It itself is just data. How you validate that data, how you find consensus determines your level of decentralization. But the data structure can be either. So yeah. Right. Yeah, exactly. Okay, one more thing I want to mention with this, just to go to the bottom of stuff. It's this on the consensus part, which is so in our design, we don't have this single leader as a node. So we need to have this quorum of nodes of the validator set, and they work together to produce a block. It's not a single node that produces a block. It's a voting system where each node sees a transaction, creates an event, they observe this transaction, they verify it, right? So then the 2/3, so let's say we're using 10 nodes as validators. 7 nodes need to put a stamp on it, on approval, that these transactions are valid and the DAG is created. So we talk about a single transaction in our example here, which is a single transaction DAG, which is not a DAG if you just look at that single transaction. The DAG gets formed when there's multiple events, multiple transactions that happen across time dynamically. And there's a time duration here of about half a second where this whole quorum of nodes observe all of these events, the transactions, and build a map, a graph, a DAG, and it becomes a very small micro blockchain that gets embedded into a block. And once that's done and all votes are received, the new block is produced. So you actually see that in the block explorer and logs, as I just showed. So this is what I will talk about next. Like, what are the limitations of DAG, and can we scale it to be more efficient? But up until now, like everything I talked about here, this is of course a lot of information to process if you're new to this, and sort out all the confusion. But none of this, just to underline that point, this is proven tech. The Phantom blockchain has used DAG tech and Lachesis for years, and also proven to be the best chain that can handle the SAM protocol stress test. So if you want to FUD us for choosing this consensus algorithm and Phantom code for X1, which again does not make us an L2, for fuck's sake, and saying that DAG is not a blockchain or some stupid shit like that, then tell me then how it's like not. Tell me like why isn't it decentralized, or why would it be less censorship resistant or less secure? Because it seems to work pretty well, and there's like an order here of how things are working, and it checks out when you like start looking in deep into it as well. Maybe this presentation, I want to have feedback on this presentation afterwards, because there's a lot going into it, and you sort of have to explain. So like you can read the Lachesis protocol, and it's going to confuse you a lot as well, because they're not very good at explaining a lot of stuff when it comes to DAGs. So we collectively have to like try. This is my attempt to try to explain this and make sense of it, but parts of it might be confusing anyway. But give me feedback on what those things were. But now, guys, let's talk about Solana a little bit again, because it's so fun. So, nice. All right, CGR, good to see you. So, yeah, that this question is probably going to be clear in the next part. So, I have done 9 out of 13 sections. So I'll probably have like 1 more hour. I hope you didn't stay up at night for this presentation because there's nothing time sensitive about it. But okay, probably should have said that before. Now, let's think about like the limitations of scaling a DAG, and if it can scale, and where it will fail, because we've seen some interesting stuff when we played around with these systems. So, because as you know, we like spanking. It's something we enjoy to do, and we like to spank things to the max and everything. And that's the only way I think you can achieve maximum pleasure. So it's really interesting to see these systems, how when you put them to like the ultimate tests, what really happens. Because we see with Phantom, for instance, it looks great, it works great, it can handle Zen, but as soon as you go in and try to manipulate the code and do something else, well, things start to fall apart. So it just means that they made some assumptions. Now, okay, so what we want to do is ultimately create a system which can be maximally decentralized, which is a stupid thing to say. I take that back, because the concept of decentralization is very vague per definition. You know, the more proper way to say it is that we don't want any unnecessary limitations to decentralization. So the network needs to be decentralized enough, sure, but it needs to be able to scale. And if we want the whole world to take part in our system, it need not crumble when more dudes enter the matrix. So, and we have observed things with both Solana and Phantom that have limit their way to scale their validator set. So in Solana, you have a bunch of junk transactions that every validator needs to handle. And this is why we doubt that Solana consensus model is very scalable with their so-called n-squared relationship to validators. So there's an excessive amount of noise, and in combination with them redlining their servers, forks happen sometimes, so it crashes the chain. Talked about this in length in my last stream as well. So just recently we saw them go down again, and not too long ago. Jack was all over it, right? The post-mortem for them. And this time, because of a bug that had been found but not properly fixed in time. Same thing happened to Avalanche the other week. I think that was the reason. It's still a bit unclear. So now let's say that we have 1,000 nodes. And generally, if we have 1,000 nodes in the traditional way, consensus would work that 2/3 of these nodes, let's say, have to agree that the transactions are valid, or 51%. So the problem with this approach is that the larger the network becomes, the slower the consensus will be, because there's simply more moving parts that are trying to work together. There's more clutter in the network. So if you have 2/3 of 1,000 nodes, that's 667 nodes. But what if we had 10,000 nodes? And why stop at 1,000? Now, the problem is that the more nodes we add, the slower the consensus becomes. And this is why in traditional blockchains, you end up being very slower with validators growing, and not only in traditional blockchains. And the terminology for this is, you call it algorithmic complexity of n-squared. So if you have 10 nodes, you square it to 100. If you have 100, you square that, you have 10,000, 100 times 100, because the more nodes needs to send more data in between. So the noise or the clutter grows almost exponentially. We try to achieve the challenge of linear complexity, which means that it doesn't matter how many nodes you add to the blockchain, consensus shouldn't slow down. Now, Solana solves this in the way that they have this concept of leaders. So they choose a leader, they have a leader schedule, and as you add more validators, the the noise in between increases with this n squared relationship that ultimately the chain has to deal with. As we can see here, like when the validators are increasing, the vote transaction has increased a lot, but the non-vote transaction remains the same or is even declining. And this is so with Solana, they have a really high so-called signal to noise ratio, where most of the transactions or events on the Solana network, their noise and only maybe 10-15% are signal in the SNR, signal to noise ratio. And that's important element in any performance metric, and Solana has the very worst one. But for some reason, they do cheat a bit because they use their votes as part of their metrics to show that they're great. And oh, look at how much transactions per second we have. Now, if we look at like two examples, so the benefits of DAG is obviously speed, okay, as we've shown. So we don't want to have to wait for a transaction to be packaged into blocks, propagated to nodes, unpacked, then verified, as I just talked about. So transactions are final right away when they're voted upon. Block insertion comes later. But there's a lot of chatter on the network because of the DAG, and the network can become oversaturated with too much noise. And this is what we can call maybe a DAG trade-off, which it's a bit disingenuous in a way, because as a node, you only need to confirm the last two events. So it's pretty scalable in that sense. But when we have tested Phantom code a bit higher up the validator scaling, validator spanking scale, we immediately see some issues. And again, I'm going to try to simplify this. So imagine two networks. We have Nakamoto consensus, and as now blocks are sent around by validators and nodes in this network. So blocks are created. There's hashes of these blocks. It's not the blocks themselves. So it's minimizing the actual data that's being pushed around, but they're being gossiped in this peer-to-peer network. Now, in a DAG consensus network, instead transaction events or event blocks are being pushed around, meaning it's a lot greater clutter since it's more transactions than in the other case with blocks. So more transactions on the chain, and you might ask, is this really necessary? So in our previous example, we had 3 nodes sharing data in between each other. But if we have 2,000 nodes now instead, moving around a lot of data, every node is broadcasting gossip like little hexagons, and it becomes a giant pain in the butt. With traditional blockchains, you just gossip the block once, and everything is done by the block. So it's lower, but less traffic. With a DAG, you have a bunch of transactions going around everywhere. So there's more messaging with DAG, with events, not transactions. So if you have 2,000 nodes, one transaction in the network, that's 2,000 events, which is a lot. And some nodes in the DAGs, it's of course observations of others, so it can be even more. And then you need consensus where all these nodes exchange observations of that event as well. So they need to observe, but also deal a vote eventually. So the point is, a single transaction can create huge many events. With Nakamoto consensus, you don't need to push events for a transaction. They just need to push a vote for a block. With Nakamoto consensus, you just have this block pushed around the network, or even the hash of the block. And then it's agreement if this block is legit with consensus. So that's the difference, of course. But how is this scalable? Because Phantom didn't solve this with their code. Like we could see that they handled the Zen protocol, double plus very good, but they only have 50 validator nodes, and they have more read-only nodes, but the chain got a lot slower with more nodes. This is what we observed. So the code only works on a particular number of nodes. So now that we have more nodes, it causes problems. The code never expected to have more than 50 nodes, it seems. So they've limited their validator set to 50 nodes, which you could argue, if you're philosophical about it as well, contradicts scalability and decentralization for that matter. So the point is, the more nodes you add, the slower the network becomes. And this is exactly what we observed in our testnet with Phantom code and this Lachesis protocol. So we can make sure, and I think that Lachesis protocol does this very well, that there's an optimized amount of event blocks being sent around in the network. But of the actual amount of event blocks being pushed around, how can we make sure that they are distributed in the most efficient way is something we need to figure out. And we think we have, and we'll get to that. But even more importantly, as we know, we need 2/3 majority for consensus. We're going for speed. We want to be fast, so we must optimize for it. If we have a growing amount of validators, that's going to mean that there's more clutter in the network. And by the way, this is a problem that we didn't anticipate when we were starting out. It's an example of a problem that arose from empirically testing all these networks, which then led to a proposal of a solution, which, while being on that path, have now a potential to be one of the things that's going to make our chain have a huge competitive advantage, perhaps. But I'm front running the solution. I need to stay in the problem. So since we have this amazing community, we got over 400 nodes on testnet, which is absolutely amazing. It was super cool to see the community engagement to an interest to become one of the testnet validators. Super cool to see your engagement, guys. And thanks for everything you've been helping us out with, because it led us to a lot of great insights that we wouldn't have reached if we didn't have this high participation, for sure. So thank you very much. Now, within a matter of a week, basically, we had 4 times more validators than Phantom did on mainnet. And this is great because it gave us all this insight. And yeah, still some people think that the whole chain is running on one AWS server in Richard Hart's mom's basement. But what we can see was that consensus struggled with much higher latency the more nodes joined this network. So when we went from 50 nodes, which Phantom is optimized for, to 300 nodes, finality went from 1 to 15 seconds. So here we can see, for instance, like how it looks like in the data. Like and this is showing on the y-axis the speed of which finality is happening. So we can see that as more validators joined, or as a transaction tried to find consensus on, or as the network tried to find consensus on a transaction, it was very fast at first, but then these same events were being pushed around so many validators. So it was flooding the network, and the finality reduced a lot. So again, the problem is more validators, slower consensus. So it's almost like it's a trade-off. Like it's fast on a small network, but it's slow on a larger network. So here I can just show you like 2 examples. So here we have a large validator set that's gonna find consensus on a particular event. So we have all these validators here with different numbers, like bam, 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 bam. And if we measure the time in between blocks here, so we have here 2:24:43 versus 2:24:48. That's 5 seconds in just this particular test. That's not acceptable. But if we limit here in the next example and select a quorum of validators, so here we just have per block different rotating validators per block, then we go from 2:29:50 to 2:29, so less sub 1 second. So the conclusion is that it has nothing to do with the throughput of the system in general, but it has everything to do with that the validator set is too big. Okay, so now how do we like begin to solve that? Like, so a good question is, what's the ideal count of validators? That's a very good question. We could see that as soon as we increased it on Phantom, it increases pretty fast, the finality. So, but this is the interesting part of how we actually can solve this. So the proper way to solve this problem is that we create an election process for consensus. So the idea is that there's no need for every validator to vote on everything all the time. It's not Sweden. So we can use a smaller set of validators for the voting. So the proper way to solve this, we think, is to create this rotating algorithm of subcommittees within the scope of the number of nodes you have in the network, where there is a segment of nodes that are rapidly chosen to work together to validate the transactions, and then they are removed from the committee and other nodes are chosen. So the network just continues to rotate the nodes for validation of transactions. So you can imagine that, what if we could have an unlimited number of nodes, but we're having these subcommittees continuously being rotated in and out. So it's like having many blockchains working together, except the choice is done every several blocks to find a consensus on what goes in, what transactions goes in for that moment, for that epoch. So if we look at this model, we have an unlimited amount of validators. Somehow there's some validator selection pool which fills the basic requirements of uptime performance. From that, we somehow create an election. So we see it as we have this magnifying glass for each epoch that creates this subcommittees that handles the consensus validation for different epoch. So remember, there's event creation, there's observation, then there's consensus, and this is what we're talking about now, and then the actual block is made. But the consensus is the part that is, when we increase the number of validators, it's slowing the chain down a lot. So this is fundamentally how Solana reaches its speed, because they have this concept of asynchronous consensus. So they don't need to wait for all the nodes to check in. They have a leader, a single node, who validates all the transactions. They publish this leader schedule as part of their consensus mechanism. You know exactly how many leaders are coming and when they're coming, and how they're being rotated. A single leader is not possible in our system, because we need a quorum that combines the decision making, creating a consensus and then forming a block. So, and remember, in traditional blockchains, you have a block producers like Bitcoin, someone who solves this cryptographic hash, proposes a block. That block gets voted by 51% of the network. If it's legit, it gets voted into the chain, and that's also what makes it slow. But because the block needs to go everywhere and get voted in. And again, in our case, we have a time frame of, let's say, half a second. We collect all the transactions. We do all the voting before the transaction before the block is produced. The voting is then done. Consensus is done. the block is then created and it's no longer needed to be voted, and that's why it's much faster. Now, the idea here is you don't have to have every node run every transaction all the time. So we can have this magnifying glass that's moving over the digital landscape of data with this focusing lens. So the number of nodes in total, it's important, not the number of nodes being chosen per block, as long as they find some kind of rotation. So instead of reasoning like Phantom, okay, 50 nodes is enough, otherwise we will be slow. We want to solve this problem by having an unlimited amount of validators in the network, and then a fair algorithm that makes sure that they are rotating. So we can rapidly shift consensus from node to node. And this is what is going to stop the bottleneck that we have from scaling, I think. So it's like we are, it's a hybrid between Avalanche and Solana in that sense, because Solana has this concept of leaders, leader rotation. Avalanche has this concept of neighborhoods. So that's a superset of nodes that have consensus of their neighborhoods. And Avalanche is also very fast. So all voting doesn't happen in the whole network. It's just in the neighborhood. So it's just like a subcommittee everywhere, where we think we should have consensus of an elected subcommittee. And in terms of consistency, that will be just as good. So Phantom is slower because on the block creation side, because you need 2/3, and that takes a lot longer always. Because while Solana has a leader, Phantom is, as we just talked about, it's leaderless, okay, which always takes longer. X1 could become a hybrid. So we have leaders by subcommittee. Every subcommittee is like a leader, and that's similar to how Solana has their leader. The difference from Phantom is that they just run one giant set of subcommittees. So we have a larger scale, or we want to have a larger scale. We want to have more validators. So yeah. Now the question is, so in summary, all what this is saying is just to illustrate that we want to have a large validator set and create a subcommittee from them somehow, okay? And that's all frank and dandy, but the question is, like, how is this election going to be made? During what kind of algorithm is that going to be chosen for? So now, what if we could? So the way to go about solving that problem is like, okay, we need some kind of formula for. Probably we need some kind of thing that measures like uptime, the internet connection. Like if you're reporting fast blocks, you can be elected in the subcommittee. We can rotate them very quickly. We can go through the whole validator set very fast if we want. If a node malfunctions or is rejected, then a new node is switched. They can also get chosen by just looking at some basic criteria and then be randomly rotated. But this would solve that problem relatively fine, but just not fine enough. Because what if we could instead analyze all the nodes continuously in the network over time, but also analyze the state of the chain over time? So is it congested? Is it a weekend? What resources are currently exhausted versus free, etc.? What if we also could predict what the state of the chain would be in the near future as well? Like, what will be important coming up? Can we analyze future needs, do some kind of predictive analysis? And then based on all that information and some framework based on criteria that would make some sense, node uptime, bandwidth, connection, etc., and perhaps 1,000 more data points, like whatever is needed as input, could then select the optimal set of quorum at any given time. And what if also this wasn't a static algorithm, but a learning model that learned from the system over time and optimized itself? So the concept of temporal dynamics. Temper refers to time, and dynamics change. So this way, we could also always have the very best set of validators validated chain at any given time. Faster finality, stronger consensus, super efficient, based on actual current data and predictive analysis of future state. So what if we could do all of that? That would be great. And it turns out that transformers do exactly that. So this is where AI can play a crucial role to do all of this for us. And in the consensus model for the X1 blockchain. So the actual consensus decision is still decentralized, but random node selection can be done with the AI model. So the AI model can aid in that. It's a tool to use to aid into finding the very best suitable validators at any given time. So the AI don't make decisions of consensus, just a section of validators that will make the consensus per time slot or epoch or whatever. So that's transformers. Now, but okay, let's just talk about transformers and understanding them. And I do want to take some time. I know it's a bit of a pain, but I do want to take some time just to read this straight up, because so you hear it from the transformer mouth itself, because this is at the heart of the chain. So it's very important. Like, what is transformers? Let's talk about that. We're going to end with this. And what are the potentials with AI? So transformers, a type of deep learning model, have gained popularity due to their effectiveness in understanding sequential data. So primarily in the field of natural language processing, NLP. However, their application extends beyond NLP and can be efficiently utilized in various domains, including peer-to-peer networks, particularly for node selection to optimize data transmission speeds. So here's how transformers can be used for decision-making in peer-to-peer node selection for faster data transmission. Sounds exactly what we want. So first, understanding peer-to-peer networks. In a peer-to-peer network, nodes or peers directly share resources amongst each other without the need for a centralized administrative system. The efficiency of data transmission in such networks largely depends on selecting the optimal nodes for data transfer. The criteria for selection can include factors like bandwidth, latency, geographical location, and historical reliability. Feature extraction. Transformers can start by extracting features from historical data on node performance. So this includes analyzing past transactions, speeds, uptime, and any patterns of network congestion. The self-attention mechanism in transformers is particularly adept at identifying relationships and dependencies in sequential data, which can be leveraged to understand the temporal dynamics, okay, time and change of the network performance. And this I wrote in here, like, not to confuse the concepts, they say sequential data. Don't misinterpret in this sense what they mean with sequential data, because every event is still sequential. Every block has a nonce. So this is how transformers are reading data on chain in a sequential manner. It has nothing to do with sequential block production versus DAG. Sequence modeling for predictive analysis. The core strength of transformers is their ability to handle sequential data. In the context of peer-to-peer networks, transformers can model the sequence of events in network transaction to predict future node performance. By learning from sequences of node interactions, transformers can forecast which nodes are likely to offer the best performance for upcoming data transmission. Decision-making with attention mechanism. The self-attention mechanism in transformers allow the model to weigh the importance of different nodes based on the context of current data transmission needs. For instance, if a certain data transfer requires low latency, the transformer model can prioritize node with a history of minimal delay, dynamically adjusting its selection criteria based on the specific requirements for each transfer. Optimization and learning. Transformers can continuously learn and optimize the node selection process. As more data on node performance is collected, the model can refine its predictions and decision-making process, leading to a more efficient node selection over time. This learning process can also adapt to changes in the network, such as new nodes joining the network or variations in the geographical distribution of nodes. Scalability and parallel processing. Giving the parallel processing capabilities of transformers, they can efficiently handle the decision-making process for multiple data transmissions simultaneously. This scalability is crucial in peer-to-peer networks where numerous data transfer may occur at any given moment. And this is why I want to read this stuff, guys, because this is like an important distinction, because the previous model was so-called R&N systems, but this is the newest shit within AI. Which is much better at handling larger data sets, and it does that by being able to process things in parallel. I'm going to mention that a bit later. So implementation considerations, of course, we have to think of data privacy and security when we implement the systems. And resource efficiency. And this is going to be very interesting if we can do some tests to see like what resources these actually consume versus what they give. Make some kind of cost-benefit analysis that never was made for the injections, for fuck's sake. Anyway, in summary, transformers can significantly enhance decision-making for node selection in peer-to-peer networks, leading to faster, more reliable data transmission. Their ability to understand predict complex patterns in sequential data makes them well suited for optimizing interactions in a dynamic and decentralized environment. Guys, this looks so cool. I think we buy it. I think we go all in for it. But this is very cool. But I don't want you to like be confused as what it really does. I mean, basically, if you boil all of that down, it's not more difficult than I think, then it analyzes the node continuously over time. Again, it analyzes the state of the chain over time. It predicts some kind of future state, or future state is probably a bad word. I shouldn't say that. It predicts like a future environment of what the future conditions might be, and then we have some kind of framework based on criteria that we feed this model with. And then it continuously learn with time and change in the network. So that's basically what it boils down to. Now, let's just mention how this actually works, like what it actually does, because I think this is fascinating. I'm not an expert at this. Jack knows a shit ton of it. I just want to get you like fluffed up, so you can handle when Jack goes like degen into this area with further. But anyway, so what they do and how it actually works with transformers, it's that they transfer bits into tokens. So they turn tokens into vectors after. So and this is creating a neural network with vectors. So they create this vector with data, and it learns which vectors work best together. And this is why it's called transformers, because it's transforming data bits into tokens into vectors. And of course, a token in this sense, it's not some ERC20 token that's tradable on PancakeSwap, but you already get that, of course. And this concept of tokens is why transformers is revolutionizing, because before with RNNs, to my understanding, they didn't have these tokens. But with this somehow, and I need to learn why, this has been revolutionary. But if you're familiar with physics, you know what a vector is. Like a vector, it has two properties. It has a direction and a strength. So let's say you have a transaction and you give that the strength 10 and a direction north. So some transactions might be more complex, but they're not too different. So they will have northwest direction and strength of 15, let's say. So vectors are then pointing in vectors that are pointing in a similar direction with a similar strength. The system can optimize for that. And if a vector is pointing in the other opposite direction with a different strength, the transformer engine will categorize that differently. And so basically what it does, it's transforming or translating heterogeneous data, different kind of data, into something that can be compared with. And this is how it can be the fundamental for them making decisions. And so it's creating this network, this neural network of different vectors, which kind of makes sense. Like that's exactly how I would do it too, if I was an AI. But yeah, so referring back to like signal to noise ratio with Solana that we talked about, like ultimately what we want and why we want to optimize this is because we want the least amount of noise, signal to noise ratio. Now, how do we do that? So clearly, we need to make sure that we don't produce so much noise and chatter on the network, okay? Because it would be useless. Now, for that, we can select these voting subcommittees that are continuously updated with this DAG system, of course, where you select a group of 10 out of 5,000 nodes, for instance. But you will only be able to select a group of 10 that can come up with a consensus in the fastest way possible. And this is where transformers come in, because this goes beyond the total stake of these nodes. For example, let's say that every node stake an equal amount. So, okay, the weight is equal, but then you want to select the best nodes to perform together as a concert in the best possible manner. So how would you do that? You actually need to analyze all their interaction, and that's a huge amount of data that needs to be number crunched. And if you're using a DAG algorithm on its own, like we do with the Lachesis protocol, like those algorithms won't necessarily adopt to the dynamic nature of the network change over time, okay? Temporal dynamics. It's so cool, this name, temporal dynamics, but it says so much, right? Things are changing in a network all the time, and there's so many factors. So being able to analyze the changes of all these factors all the time, like you can't just put that into an algorithm that's going to be static and be optimized for the rest of the time. You have to be able to change for new information. There's this saying, like a static vision is a function, is a result of a non-functioning learning process. And I love that that quote. My uncle told me that when I was a kid, and it just stuck with me. But it's the same thing here. Like we have to adapt to the changes of the environment. We can't use something static. So how would we do that? We need to analyze the interaction. We need something that can handle timing change. So it's constantly learning the change in the network. And you need to have predictions as far as which decisions you make based on what you know of the network. So for example, the network could be dissected into quadrants or confederations. That confederations could be assigned some kind of quality score. Like this confederation is very good, so most of the validators are chosen to create consensus from that zone, and then the nodes promoted here and there based on their performance over time. So this whole confederation management is done by the transformer engine, okay, that continuously evaluates the state of the network and then learns from it to make even better decisions over time. It's most likely, I think, we need to ask Jack about this stuff, but it should like tax the system somehow without this computation. But it's going to be very interesting to test this out and to see. I think Jack already has like an idea or has the script in his mind already how to implement it. So let's hope that we can play with it very soon. But the way this transform engine works is that you're basically having an input, and the input is could be like analysis of user patterns and availability of resources, for example. And then the output is the decision making. And in our case, for selecting validators who will in turn be the best suitable to find consensus for any given time. So it's not like the AI is doing all of this, it aids in the decision making. It's a very important distinction to make. And yeah, again, this sounds very complex in a way, and it's AI is very new to a lot of people, but it's complex because it's new, of course, and it's complex in the sense that the computations that it does is like way above my math grade and brain capacity, of course, and all of yours. But what it's doing, it's basically pretty straight up in that sense. So, and the effect is like huge, of course, if you just like scrape the surface of this and try to understand I mean, when you think about it, like, okay, you can analyze like thousands of nodes over time and adapt to change. It's like, of course, you need to optimize that. It's sort of like given if you have the possibility to do so. So I just want to regurgitate, or however you say that name, that like that's like how. Give some examples. I mean, we have some time. It's not time sensitive, so if you want to go to sleep, you can go to sleep. But I wanna go to some bottoms with like two examples that Jack brought up in the recent Twitter Spaces. You should really go listen to those when he explains it. And I know that Jack's not going to be able to shut up about this. Like, we're really excited about implementing this, and I'm going to tell you why as well. But why? Let's give some examples. So Jack brought up this example when he was in charge of the data centers at Google before they went full woke. So they needed to make sure that this was way back in the time. As we know, Jack was like super early in Google. It's very interesting in the sense that he has been in open source tech for decades and also worked with like large scale systems that needed to be optimized, and he was like the guy to do so. So he has some experience on this topic. But anyway, they needed to make sure that Gmail got a higher priority than web crawl. And this web crawl thing, it would often stamp on everything, and it affected Gmail. So you couldn't log in to Gmail when web crawl was running. So the problem was that it was impossible to know when web crawl would start and how many resources it would take based on time of day, whether it's weekend or a weekday. So they had to prioritize traffic based on resources, based on user patterns. And of course, so with a transformer engine, user patterns and availability of resources is this input that we can have here. And then the output is decision making, is like what kind of buttons you could push to make the system run faster and accommodate the load based on demand. But this transfer concept was invented much later, I think by Google itself as well, if I'm not mistaken. But that's a situation where it could have been good for optimization of the network. Like when you have two things that are sharing, two functions that are sharing the same resources, and you don't know when there's an uncertainty that's very hard to predict over what the user patterns are for function A over function B. So what the AI engine also could do is then observe the network over time and see if, in our case, if these nodes are coming up and down, and it can build some kind of routing table more intelligently, so our gossip protocol runs faster. Or neighborhoods, where each node, based on its proximity and capability and availability, can improve the overall throughput. So that's the most basic thing that it can do for us. And all we need to do is then create these AI agents to observe the network formation and create these neighborhoods intelligently. And with transformers, the biggest difference is that a lot of these decisions can be done in parallel. For example, you can take in consideration the node's uptime, how fast it is. It can submit its speed of transaction processing at any given, and give it a rank. And how fast is the network activity, what's its latency, and also the stake. Are you staking XM enough to take all that load so you can get the transaction fees? So just running the network more efficiently with AI together with DAG, and this might be like, as Jack explains it, the holy grail of a consensus mechanism. So like all peer-to-peer networks are heterogeneous in nature. So if we're adding AI into aiding the decision-making of how those transactions can be routed, that would be very cool. Another thing he brought up is the fact that, like many think that a node, it either works or it doesn't. But what he learned at Google and was that a lot of times the worst position to be in is when your node experiences a so-called a brownout. So it's not the same as the blockout or an outage. An outage or blockage is of a node is a good thing because it's very binary, right? You know, it's offline or online, and then you can remove it from communication for a period of time. But when you have a brownout, you have a situation where half of the network sees your node and half of the network does not. So one portion of the network sees your as fast as handling transaction is fine, but the other side of the network doesn't. So if you put it all together, the blockchain performance suffers based on this worst component within the system. But the problem here is that it's super difficult to come up with a decision as to what to do with that node. So because one part of the system thinks it's fine, the other does not. So you have a conflicting decision leading to indecisiveness, so indecision, or even a fork of the chain. What is supposedly called a split brain. So when these decisions are split, the blockchain performance suffers, of course, and we want our network to be extremely fast. So I think you can like figure out right away that there's a bunch of scenarios where there's a lot of uncertainty if we have a decentralized node network that's going to perform various tasks under extreme load. That of course these systems lately like tuned in to the max. Like I think we should see it as like we're building a Formula One car, not even a Ferrari or Lamborghini. It's a Formula One car. And if you see in Formula One cars, like these guys, they have a driver which is like super focused only on driving. But then you have a team of like 100 people sitting behind screens, watching, analyzing the performance of like every little detail of the car. Like some guys are only specialized on the tires, some are only specialized on the engine, some are only specialized on the chassis or whatever. So we need to have like this we need to treat the chain just like we would a Formula One car. I think that's how we should look at it. Like analyze every little thing and optimize it to the max. Like with time. Now we're still like moving around large sets of blocks. Like, should we have this consensus mechanism or that? But now it's really interesting because now we're like in the heart of the Lachesis consensus mechanism and the stress testing it. We're pushing the boundaries. We're putting in a bunch of validators. We've done a bunch of tests with inscriptions. We haven't talked about that, but we've done a lot of that, and it's coming. So, like, yeah. Anyway, so referring back, like what we see in Phantom today and over history, they have a limited number of nodes, okay, within that network that could become validators. However, as like they then probably have like a bunch of read-only nodes, as many as you want, but and these nodes are read-only nodes are also very important because they sync the chain, they unpack it, they go through all the verifications, verify all the transactions, and make sure it's all correct. So they're also very important. But now we're focusing in on the validation part. And if we take this as an example with Phantom, the decision making there is limited to this 50 nodes, and the need for them to analyze is maybe less, because if you have 50 nodes and let's say one goes offline, well, they can just remove it, and that's it. So when you have 50 nodes, it's fine. But if you have like a lot more, if you have a lot more, then it's a lot of moving parts. So imagine now if we have like 5,000 nodes in the network, and you have a lot of moving parts, and a lot of nodes come up and down. You can't watch them all just because you don't know what will happen. And here we can implement this adaptive AI technology using transformers, where each node then observes the rest of the network using AI models. So the model, the way I understand it, is like some kind of script that is embedded on each validator node's set of code already. So the whole transformer engine is this decentralized network, and yeah, we can then make like the ultimate decisions as to how do we select this validator set to make decisions as to how do we choose the validator set, and then to be the most optimal possible, to find consensus, to validate and make the transaction final as fast as possible, as reliable as possible, as optimized as possible. So yeah, let's see how that goes. Now, I just want to mention quickly as well, I'm not going to read through all of this, but separate between RNN and transformers. So when we look into deeper, we're going to talk and we're going to hear about RNN. RNN is recurrent neural network. RNN is old tech, and everyone is using transformers now. So there's a difference here between them. You can just screenshot this page, perhaps. I'm going to remove myself. Or just ask ZenGTP. ZenGTP should be up now again. It was down because there was something wrong with it, but it's back up now again. So you can go to ZenGTP if you have 1 million Zen in your wallet and ask it what's the difference between RNN and transformers. But basically what it comes down to is that RNN is the previous version. Transformers are way more advanced. They can process entire sequences simultaneously, which makes them very suitable for large data sets, and they're more scalable. So now let's talk about something fun for a change. So it's this whole AI narrative that's exploding. Because and why is it so? Well, it's not so difficult. Like AI in itself is very cool. It's cutting edge technology being merged with the blockchain. Of course, it's very cool. Now, The thing, though, is that everyone is trying to use AI for external applications of the chain, like storage, data analysis, prediction analysis, creation of models, or rent of GPUs or whatever. But it's all external. And what they're doing is trying to link the blockchain to the economic principles to AI. Sort of like we're doing with ZenGTP, right? It's an AI thing, and we're linking it to Zen. Like Zen, you need some kind of Zen in order to use it. That's the difficulty to getting to use it. But they don't really intercept. Like the AI technology has nothing to do with Zen and vice versa. It's just like intersecting in an application. So what most of these things are doing is that they're at the application level. And every blockchain, everyone in the blockchain, their consensus models, they're just following these like static algorithms. And they're having their static algorithms for how validators are rotated and chosen and whatnot. What we can have is this learning engine that can select the best nodes for the DAG consensus mechanism. So what we can do, like if we do this is what's cool, without hyping up anything, but it's just what it is. We can use AI in the consensus engine of X1, like in the heart of the Formula One car, which is what no one has done before, to our knowledge. So no one is using the consensus algorithm using AI itself. So AI in blockchain tech, as I said, they're not really intercepting, but we have an opportunity. Americans love the word opportunity. We have an opportunity here to use an application, AI as an application, not only to use AI as an application of the blockchain, but actually have the blockchain speed and performance directly benefit from the most recent AI discoveries, which is basically transformers. And this is this year. Next year it will be Xenobots. So, but anyway, so we can use transformers in blockchain consensus selection. We can use them for helping in the decision making specifically, and we can learn what the conditions are in our peer-to-peer network over time. Temporal. No, I even forgot what it was. Guys, did you remember? Temporal dynamics. For fuck's sake. Temporal dynamics. With temporal dynamics. And with temporal dynamics, we can have the AI model help us in choosing the best set of validators at any given time based on the conditions, the history, the performance, like whatever. I know I have some friends who are making like websites. They're helping companies do their UX just by analyzing user patterns on their website, and they're looking at like 1 billion different data points in order for, and that feedback is then given back to the customer to like say, okay, I'm going to put this button here or here or there. So once you have that in place, there's like whatever are the things that we want to observe that can be observed, and to help that those metrics to analyze all that data. There's a huge amount of data. There's a huge amount of people. We shouldn't have any limits to the amount of validators that can join this network. But in order to be fast and execute, we need to limit the amount of validators who are in charge of the consensus at any given time. This works very well to the most part, like with Solana, to have this leader selection. It's that leader function in itself is very efficient. It's very good. But then how it's implemented and with their consensus mechanism, that I think we have an opportunity to do something better. Let's see. That's the goal. And also the last the last thing I want to say is basically that something that's interesting to think about. Like, let's not forget also the benefits of having a proof of stake, proof of work hybrid chain as well, because we have a proof of work layer that's huge decentralized. I think it's a huge success with Zenium and Sandblocks. It's just like this pure crypto implementation, and it's filling a great function for X1. So we have this huge decentralized networks on its own, with what will be, I think, like if we follow this trajectory, thousands of miners. And what do? They utilize GPUs for finding blocks. And with these machines, they also come with CPU and disk space that's underutilized at the moment. So these are resources that can be used for the network somehow. And we also have this huge decentralized network of validator and read-only nodes as well. I mean, we just killed it as a community, guys. We have like hundreds of validators, like quickly. So the demand is there to build this network together, which is awesome. And that's also another like huge computation resource. So this makes sure that we can stay decentralized and secure over time. We need the best mechanics in order to facilitate that without being the consensus mechanism being a bottleneck for our growth, because we have the interest, we have the community, and this enables us to scale by having a huge validator growth, for instance, in a non-N2 squared way. So, but with linear complexity. So the network won't slow down if more validators are joining. And on top of that, we can use the AI models like transformers to make sure that the entire network is optimized. I mean, fucking hell! Like we should make a crypto. So I hope this like gave some more clarity in like I hope you like appreciate the segue into transformers, like based on a real problem that we actually have and we need to find a solution to. It's like, how do we optimize the validator set? The rest of the tech is proven, it's fine. X1 is going to be great in terms of being able to handle transactions with near instant finality, etc., etc. Yeah, give me some feedback, guys. Like, what's the confusion around these topics? We talked about the benefits of DAG that we've seen from empirical like testing, and here's the receipt of that. The chain Phantom using DAG and Lachesis protocol has worked very fine. We talked about what is a DAG really, how can we look at it from a data structure perspective. We looked at the limitations of sequential block production. Let's not at least fall in the same traps as the other systems, these dinosaurs. But let's be compatible with them still. You know, it's still important to have compatibility with the whole EVM world and also Bitcoin. We're not going to go the Solana route in that sense and be like an isolated system, which I felt for a lot of years, especially last cycle, that all these L1s are trying to do like the Pulse way and say that, or the Cardano way, and say that, hey, we are much better than you on XYZ. Come to our chain, and we have to spend a huge amount of resources in attracting people to go there. We think that these systems, you need to be interoperable with all of them. And this is why we have this token distribution on these 13 EVM chains, because it gives the user a choice that for many years to come, you can come into X1. Actually, you have a financial incentive to do so. Stay on your chain, create your send there, burn your send there, but come to us and have fun in the Ferrari. In the Formula One. So we talked about transaction finality, Nakamoto consensus, DAG consensus, and that the finality happens before the blocks is actually produced. We talked about asynchronous Byzantine fault tolerance, and all of that shebang, and some new terminology for some, like we're creating these DAG structures, and from that, then we're the validators through finding consensus, are creating this block. The heart of the engine, the Lachesis mechanism, it's asynchronous, leaderless, recently fault trodden, and final. It's the properties. We talked about the transaction lifecycle. We showed in detail how all of this works. I might fucked up something I said or whatever. There's a lot of information, but let's use this as a foundation and then learn together how it all works. The DAG trade-off, like the limitations we've seen in our tests with this, and that we obviously want more than 50 nodes. How do we solve that? We solve that by having elections. And how do we select the subcommittees? This is where transformers come in. Bam! And we need to learn about transformers, read everything you can about them, share your experiences with the community, like what is the potentials, who else is using transformers for what can we learn. This is basically how it works. It transforms database into tokens, into vectors, and then it has some switch the heterogeneous data into something that's comparable, and that's how it can aid in the decision by taking inputs from the network and then helping in the decision making from the outputs, how we can select these quorum of validators. Super interesting, guys. Things are coming together nicely. Yeah, I think that's it. What do you say? X much be launched before the bull run is over. Yes, we're highly aware of it. At the same time, you know, like if you think about everything we've done, that's the way I think about it. Is the fact that it's the fact that, you know, I'm very happy. Now, if you look at what we have EVM compatible X1 chain. We are on 13 EVM chains plus Bitcoin. We're going to be able to process millions of transactions per day. We have near instant finality. We have a proof of work, proof of stake hybrid in a sense. We have a fiat on ramp to X1 through Zenblocks with miners without KYC. We have compressed rollups for inscriptions. And we have AI transformers, engines, and consensus model. So yes, things take a bit of time, but the Formula One car we have now, oh my fucking God, the Polygon Edge fork that we were planning to do last year, that's like driving an old Impala with like rusty doors, and you know, you don't get any honey bunnies with that car. Now we have a Formula One car. So I think we're looking at things very long term, in the sense that what we are building should be able to be a great system decades from now. But of course, we're highly aware of the bull market and the momentum that needs to be caught there as well. So this is where liquid staking, which is another thing that's very interesting, that can be something that potentially can be like accelerated. That's something we're discussing right now to capture. So yeah. Pac-Man, are you the founder of Blur? Non-believers like Pac-Man. He blocked me. Okay, unblock Rolando. Rolando, you can't block. Nice. Let's go. Yes, Pac-Man. Let's do it. Flux capacitor. What's that? Capacitor. Okay. Time traveling. Yeah, exactly. That is what we're building, a flux capacitor. Oh, is it from Back to the Future? Yeah. Yeah, here's a flux capacitor, or whatever it's called. Capacitor. Yes. Guys, do you have any questions? Y'all have a lot of homework to do when it comes to learning about transformers now. Keep on giving a good data in the validator group. Will validators be selected based on staked amount? Yes, I mean that's part of it, right? So we create this. We need to create this thing. It needs to be a criteria-based selection, and this is where the transformers and the AI help in it. But stake is obviously going to be an important part of that. Then what weight your stake has in relation to like your uptime and performance and bandwidth is still to be iterated. Thank you, Pac-Man. We just need to be on SendGTP. Yes, exactly. In Echoes of Realm, where shadows play, a tapestry of light, now dim, now bright, reflects a world and snarred in an endless night where truth and fiction mingle and decay. Dude, edibles kicked in on you, didn't they? Yeah, Jack, did I get this right? There's probably a lot of stuff that, yeah. Sorry guys, I didn't follow the chats so well, but yes, we need a Formula 1 car. Benny Blanco is in the house. Cutting edge. Yeah, it feels good. Feels good. Yeah. Jack, is that a SendGTP poem or Hunter's Thompson quote? his AI is on the edibles. All right, guys, this has been fun. A lot to cover. It was some time ago. I did a stream. I've just focused on just reading, studying these systems. Like once you start like opening up, it's super interesting. Most excellent TikTok. Yeah, because I copy everything you say and then I say it on stream. Yeah, Joseph, good to see you, buddy. Good to see you. All right. So guys, LFG, Bitcoin. Let's just check what Bitcoin is at before we go to bed. 61,573. We have Ethereum at 3,400. USDT $1. Interesting. And yeah, guys, we're closing in on an all-time high of Bitcoin. What is it? 67,000, if I'm not mistaken. So yeah, that's going to be interesting. Okay, guys, thank you so much. LFG, LFSEN, LF, let's fucking hash, and all of that. And stay sun. Stay sun. Let's work link up to red candles. It's only a way they don't believe. Oh, Rome is in the house. Yeah, it's only up from here, guys. It's only up from here. Don't quote me on that. Thank. Okay, guys. See you. Over and out. Now I'm gonna drink some water.